So we are going to talk about our last section here. This is called Exponential Models. And this is definitely a fascinating time to be able to talk about exponential models. These pictures that I'm going to be using were taken off of Bing's COVID-19 Tracker. And it was April 7th in the morning. And this was the number at the time, and as you'll see as we go through this, these numbers change rather rapidly. And so this is just the afternoon of April 7th, and so I'm sure the global status is higher. This number represents the number of confirmed COVID-19 cases in the world, and you can see the bigger bubbles are the higher density of the virus. So we're going to talk about this in terms of growth rate, and the name of the section is exponential models. So really most of the time we're going to do models of exponential growth or decay. I am not going to do a whole bunch of examples out of the book this time because, we have this situation going on right now, and we're going to play around with the numbers and take a look at that. But first we need to get some definitions and things out of the way, so let's do that first. So there's this idea that I think you can wrap your heads around, that there's a lot of quantities around us that have this situation where the rate of their change is proportional to the amount of the thing that we start with, and so the easy thing to think about is a population, right? The more people or whatever there is, the quicker the population would grow. Two people can only have one kid at a time usually, but 1,000 people can have way more than that. And so if we start off by saying that we have this function, it's a population function with respect to time, then just think of what your derivatives mean. The derivative of that is actually the growth rate, and then they call it the absolute growth rate on top of that. And so since it is proportional, since the growth rate and the population itself are proportional, we can set it up in this fashion. And this is just the kind of like the definition of proportionality. And so we're saying that, the growth rate is related to the population proportionally by this constant k. So what we're going to say from here is that, we can actually solve for, this is a differential equation that we can solve for, and we need the idea of separable differential equations to be able to do that. So let's solve this and see what happens here. And so I'm going to ignore k for this example here, or for this explanation. And so I'm going to change this to dy dt equaling y for right now. And then when we separate these, we're going to have dy over y equals dt. And then we're going to integrate both sides. I guess I'll just do it here. So, we're going to integrate dy over y and integrate dt. And when we do that, we're going to get the natural log of y equals t plus our constant. We do want to solve for y here, so we're going to switch the form, and so then y becomes e to the t plus c, and we can, if you want to see this, right, this would be the same as e to the t times e to the c. Well, that's just a constant, right? So we're able to just change this to our constant letter C, and we can write this as y equals our constant times e to the t. So this is a general exponential growth formula, and when we have this, now we're able to really play around with some really interesting models. And so that's what I'm basically going to use this variation of this formula to talk about the spread of the COVID-19, and this will pretty much cover everything that you guys need. I am going to do one example out of the book to compare linear and exponential growth, and talk a little bit about relative growth. So I am going to do that first. So this is a variation of the one in your book, but you'll get the idea. So what we're being asked to do here is show that the growth rate of the linear function is constant and the relative growth rate of the exponential function is constant. And we'll talk about the relative growth rate, the definition of that here in a second. But this will be our linear function and our exponential function. Right now these are just population models. Right, when we take the derivative of these, we're going to find the growth rate. And so let's do that with the linear one here. Okay, and so then when we take the derivative of that, we find that it is a constant at 400 in this case. And that should make sense by looking at the function here, the original population function. We started with a population of 2,200, whatever you want to think of, like people in a town or bacteria or something like that. And then as each time interval, or as the time interval increases, so every new time interval we add 400 more. So maybe this is per month if this is a population of a town. Every month 400 more people show up. Okay? And so no matter what goes on as we go forward, it's always going to just add 400 for every interval. So we're going to move over to the exponential one, the exponential model, and when we take the derivative, again, we're changing that into a growth rate at this point. And when we take the derivative of this, right, we still have this whole exponential part going on here. Okay, so the growth rate is still dependent on the time. It's not going to always be constant here. Something's going to change as we increase our time. And so this is where the definition of relative growth rate comes in. And the definition of relative growth rate is the growth rate, which we just found, divided by the current value of that quantity. Okay, and so then they write it like this. Oops. The growth rate, well, I better use G in this case. So for our problem, the growth rate divided by whatever value we are at currently, okay? And so, again, this is what we found as our growth rate, and we're going to divide it by this is our population at the current time t. So when we plug that in, you see that the e to the t over 20 cancels, and we're left with 20 over 400, which is 1 over 20. And what that's telling is, our relative growth rate is 1 over 20, and so that means that it's increasing at 5% in a way. So it's kind of like a compound interest thing, right? As more, it's always 5% increase of whatever the current value is. Okay, and hopefully I didn't misspeak over here. I think at one point I said that this is a constant, and it is a constant, but that means it's growing linearly. So I hope I didn't misstate that. So that's the idea. Now we're going to talk more specifically about exponential growth and the situation we find ourselves in right now. So this is, I guess the definition of an exponential growth function. And there's a couple new things that we've come in, that we've introduced here. T is still going to be our time interval. And so now we have this y sub 0, which is going to be the initial value of the situation. So think of whenever t equals 0. And then k is going to be called the rate constant. And that determines the rate of growth. And so I'm going to talk about the rate of growth first. And there's this formula, and you're welcome to look through the book to see how it was derived. But it's called a doubling time formula. And it's denoted like this. And the doubling time is found by dividing the natural log of 2 by our rate constant. And, this is also the same formula, really, for half-life. So, some of these problems will turn into half-life, and then it would be denoted this way. But the actual formula is the same. Now, our rate constant in a decay would be negative. So it does produce it okay. But I'm going to just talk about the first one. So let me get rid of that. But do know that that is the same. I don't want to get rid of all of it. Oh well. Let's bring that thing back. And so let's bring this back. Okay, and I'm going to show you a couple different ways to set up an exponential growth model. So let's do a couple examples. And so I looked up some things, and what I found was on January 14th, so January 14th, there were 3 confirmed cases of COVID-19 in the United States. So we're going to start with that. And then the other thing that I've heard is that the doubling time, I heard this one that was concentrated heavily in Washington, D.C. area. They said the doubling time is between 3 and 4 days. So we're going to have that also. So 3 to 4 days. And again, what that means is whatever we're starting at, every 3 or 4 days, the population will double. And so in our cases, the amount of infected people doubles 3 to 4 days. So we're going to use 3.5 days for our example here. And so here is a way to set up a couple ideas. This is the first way I'm going to show you on how to create our exponential model. And so we're saying right here that this is our y sub 0. That's our initial value. Day 0 was January 14th. Okay? Now, you notice that we do have to get this complete. We already found that. That was pretty easy in the case that we're using here. Now we're going to find k. And we're going to use our doubling formula, our doubling time formula, and the fact that we're saying it's about 3.5 days to double. And we're going to use that to find k. So our doubling time, we're going to say, is 3.5 days. and that's going to be the same as the natural log of 2 over k. And we're going to use that to solve for k. So then k equals the natural log of 2 over 3.5, which is approximately 0.19804. Oops. Okay, so to try and be neat with my writing here, I'm going to use this in our formula, but when you compute things, you want to really use the more exact version at all times. And if you think about this, when you round something and keep reusing the rounded information, you get further and further from the correct answer. And so if we keep using this as our time increases, then we're going to get further and further from the exact answer. And so in the calculator, when I did all these problems, I used this, but I am going to write it like this because it'll look a little nicer visually. And so then what we're saying is our exponential model, and we can use it, we'll call it COVID, is our initial value of 3 cases that we found, e raised to the 0.19804 t, where t is days. And so in order to project forward, all we're going to need to do is say, well, how far forward? Now this is where it's going to get a little bit off, and we're going to talk about that here a little bit. But as of this morning, so again, April 7th, I believe that's 84 days later. So then we would say, well, how many cases are there 84 days later? Right, so we're just plugging that in. And what we get is 50 million. Okay, and just to put a little fine point on the reason that people started panicking when they started looking at these numbers is they're saying about 5% of these cases become critical, so end up in the hospital or death. And so 5% of 50 million is, so like if we, let's put this away. So 5% of that number ends up being 2,516,582. And that's the critical. And so, and again, like this is really amazing numbers, really, because we're talking about the doubling rate being 3 to 5 days. And so, I started playing around with this idea to do this video this way on Sunday. And of course, the numbers were different, a little bit different, but, in just like a couple days, I don't remember the exact numbers, but this critical number was, actually I have it here, was 1.7 million. And so like that many more by the numbers are working. Now, of course, you may be saying, well, those numbers are not true. That's not what's going on. And what you want to keep in mind is that, well, there's a couple things to keep in mind. One is that these are numbers assuming that everything just keeps going on at the same rate. In a lot of places we've started this, especially in Ohio, we've started the social distancing. They've closed down schools in order to get a handle on these huge numbers. I mean, like, this is crazy. And people will say, well, why are we worried about it? Well, if this many people start showing up at the hospitals, we're in trouble. And I've seen some numbers that are crazy. In the county that we that you guys are living in, this is a county in Ohio. They're talking about at the peak right now, at the peak, that they would need 145 hospital rooms per day, and they have two. They have two ventilators now, and that's per day at the peak. They're worried about needing 145, and so this is the reason that people luckily we have a governor that decided to close these things early because of this stuff. Again, this number isn't exactly working out, but this was the beginning of when people were like, "Oh my God, we have to do something about this because this is, this is unsustainable." Now, the other thing to keep in mind, and I'm going to talk a little bit more about this, is that things don't grow exponentially forever. They do at the beginning, and that's what we're seeing right now, but then they end up plateauing off. And so I'm going to talk about this again. You'll probably hear me say this again, but when they talk about flattening the curve, for us, that means they want to turn this more into a logistic type equation. And we've talked about those before, and I'm going to show you some examples of that. But I do want to do another example. So I'm moving to the state of Ohio now. And again, I got some pictures I'm going to show you guys that illustrates a lot of this stuff. But instead of cases of positive COVID-19 sicknesses, I moved to deaths. And so this is April 7th, but the information I had was only through April 6th. Obviously, April 7th isn't over right now, so they wouldn't know this amount of deaths. And so the first recorded COVID-19 death in Ohio was on March 20th. And as of yesterday, for this recording, there were 142 deaths. And so let's create a exponential growth model based on this information. And the difference is that we don't know the doubling time right now. Okay, so what we do have two bits of information that are going to be very useful here, and that's our initial value. So our initial value here is 1. And then April 6th is 17 days later. And we're at 142. Okay, so we're going to start with our same beginning information here. And we do have to find two new pieces of information. And we need to find K and our initial value Y. The initial value Y is not going to be hard to find. I mean, we already have it up here. Right, we already have it right here. But I am going to go through the steps so that you can see what you would do. So what we're saying is we're just substituting this in, and it's nice that our time is at 0 here. So when there was 1 death, that was at time 0. And why that's nice is because, as you know, this will end up becoming 1. And so then right away, we can say that our initial value was 1. And now we're going to use this second bit of information to find K. So I'll try to do it without zooming down here. So now we're saying there's 142, initial value of 1, K times 17 now. And so then we're going to solve for K so that we can set up our model. So we're going to take the natural log of both sides. And divide by K. And, the approximation is, where'd it go? 0.29152. And again, I'm using this value to write the equations, but when I do all my computations, I'm using this more exact value. So now what we have is our exponential model for deaths in Ohio. and t is still in days here. Our initial value of 1, so I'm going to leave that off. So, we have this date of May 1st where, we're going to be reevaluating, I'm going to say, our situation. So let's see what the deaths will look like then, and see what we may think of that according to our model that we just created. Now, May 1st is a Friday, so we wouldn't be back in school on that day, I'm going to tell you. So then it would be that Monday, which would be May, let's see, so first, second, third, May 4th. Okay, and so then that would be 45 days after the first death on March 20th. So we just plug in 45, and then we find that on the day we're supposed to be going back to school, our model is predicting that there are 498,000 deaths in Ohio. Whatever you guys want to think about the fact if we're going back on the 5th or not. Now, obviously, well, I'm not going to say obviously about any of this stuff, but I really hope that we do not have anywhere close to this many deaths. But according to our numbers, that's kind of where we're talking about. Another thing that we can do that I wanted to do here is we can actually find the doubling rate. So let's do that also. Now that we have our K, we can find that really simply. Oops. Stop. All right, so then our doubling rate according to our numbers, and these are relatively accurate numbers here. The doubling rate as of right now, because we are using the most current data. And again, when I did this computation, I used the more exact value down here. It is approximately 2.4 days. Okay, so think about that. We had 142 deaths as of yesterday in Ohio, and that means on Sunday we had 71. Right, and then on Friday we only had 35 or so. Right, that's an insane amount of doubling, and so that's how we can get to such a big number so quickly. And I told you earlier I was playing around with these numbers on Sunday, so just a couple days ago, and I was really hoping that all these numbers would work out a little more accurately. And at the time, the model I did predicted only 516 cases in Ohio, and this is not deaths. This is back to just how many people had it. And on Sunday, we had 3,739 cases. And I was like, oh, man, that's too bad. But if you think about it, it's doubling. So, it doubles from 516 in a couple days, then it's at 1,032. And then it doubles again, it's at 2,064. So, like those numbers aren't really that far off, which is just, very amazing. Now, we have talked about these logistic formulas, and so I want to kind of tie it together with that. So this is an example of a logistic equation, and it's based off of a famous curve, and then there's variations of this curve through, the parameters change, and so they talk about different things. But this is Richard's curve. And it's really cool. If you go to Wikipedia, you can go to and look up Richard's curve, and they give you graphs that you can manipulate by changing the different parameters. And so this number here was the population of Ohio in 2010. I believe Ohio has increased its population, so this number is not what it is today. And then this is this part here is our formula for, or at least very close to our formula. We have this negative here for our exponential model that we found. And, this is called the carrying capacity. Now, like if you really want to be frightened, you see what happens. Like if you take the limit of this function as t goes to infinity, what you'll notice is that this value just goes to 1. The denominator goes to 1. And so then as t goes to infinity, everybody in Ohio gets COVID-19. Now, again, that's not how it's really working. There's people, we're doing a pretty decent job, especially compared to some other states, of keeping apart from each other. Again, luckily, Governor DeWine told us to stay away from each other and close schools down and non-essential businesses. But we can't have 11.66 million people in Ohio catching it, because, again, 5% of that is an awful number of deaths that we would have to deal with. And so, there are, and again, this number wouldn't be accurate even if that was the total, because there are people that are immune to it, naturally immune to it. And again, this isn't factoring in the social distancing, and that's really our only option at this point. So I want to show you a couple other pictures as we go and to illustrate all of this. So again, these pictures are all from Bing's COVID-19 Tracker, and this is for our state of Ohio. These are confirmed, and it's in the linear mode down here instead of logarithmic. And you can see as we're creeping along, early January, nothing, and then it's really taking off, right? This is a total exponential curve here. These are our deaths, but right, 142, what we talked about. And so that's an example of the curve. And again, it will end up kind of leveling off, right? It'll have that logistic look, and I'll show you an example of that here in a second. Here's the spread of the virus in our state. Where we're at. Oops. Where we're at over here somewhere, right? The darker is the heavier one, of course, in the major cities, right? You can't get away from it, people as easily as we can around here. This is just a picture of more of North America, with the biggest dot there as the New York, and Louisiana down there is bad. And so this is just a zoomed in picture of that. And if you go to Bing, this is basically the bottom half of that last slide. You can see that, unfortunately, right now we are way out of control. We're already over 10,000 deaths. And this is, if it's still on there, this is China mainland. And this is the, kind of the example that we have for the logistic model. Here it goes exponentially, and then it peters off, right? Only so many, the virus cannot spread if it can't have any other human hosts. And so we will see this peter off. This is flattening the curve. You can tell me that China isn't giving us good information, which is probably true, but eventually it will peter off. But I think the point is that please stay away from each other for a while until we can get this under control, so people don't have to die unnecessarily. But this is an example of the logistic model in action. And again, I want to say that our numbers aren't exact. The things that the medical people, the CDC, are looking at, they have a lot more parameters that they can enter in. And, this is when they tell you, if we can just stay apart for a couple months, we can really have a huge effect. because that's one of the things as you guys are working through these problems that you'll see, like little changes at the beginning really make a big difference later on. So be safe out there. There is one little thing going on with the way the book is asking you guys to do your exponents, and I'll post that as like a little explanation later on. But be safe and take a look at these and see what you guys can do.